We've got the platinum group elements, ruthenium, rhodium, palladium, osmium, iridium, and platinum, plus gold and silver, and also some elements that aren't precious metal elements like mercury, copper, nickel, and cobalt. These are all the elements that David Hudson, one of the early pioneers of ORMUS research, first discovered, first noted that they have this form. Now, how would we know if this substance was a connector? How would we demonstrate that it's a connector? How would we demonstrate that it's capable of non-locality, capable of quantum coherence, and so on? Well, quantum coherent behaviors include such things as superconductivity. A superconductor is a quantum coherent structure. But scientists say that, most scientists say that there are no room temperature superconductors. That in order to have a superconductor, you have to cool a substance to approximately the temperature of liquid nitrogen. The air we breathe is mostly nitrogen. So if you liquefy the air we breathe, that's how cold it has to be. It's not that cold anywhere on Earth. Even in Antarctica, the air is always a gas. It never liquefies. Even in the upper atmosphere, it doesn't liquefy. It's always a gas. So in order to get liquid nitrogen, they have to really, really cool, super refrigerate air, and that's the temperature at which they say superconductors happen. Now, how do they measure superconductivity? What's the criteria? Well, the thing that they do to figure out what is a superconductor and what is not is they'll take the superconductor or the lead superconductor and spin it over a magnet, or spin a magnet over it. And a superconductor will repel the magnet. Doesn't matter which pole of the magnet. You can turn the magnet over and it'll still repel. Now, if you have two magnets and you try to put them together the wrong way, one of them will jump away and slap back like that. But that's just ordinary magnetism. A superconductor, the magnet will levitate, and you can turn it over and still levitate. They call this effect that makes it levitate the Meissner effect. And what they say is that the Meissner effect excludes magnetic fields. It excludes magnetic fields so that they can't get in. So anything that has a strong magnetic field, it will be repelled by it. And in order to do that, these superconductors have to be coherent. All of the atoms in there have to be in a matrix that has all of them sharing their electrons and in some way or another all coherent, so that they're... Now, I'm going to show you an example of this stuff levitating in a magnetic field. This short video shows what we think is superconductive magnetic levitation of ORMUS gold. This video was shot on July 25th, 1996 on my kitchen table. The ORMUS gold was made from metallic gold chloride using ozone. The only materials used were commercial gold chloride, salt, hydrochloric acid, bicarbonate of soda, distilled water, and ozone. I am placing the ORMUS gold on a piece of paper which has been folded to make it more rigid. I will be moving a rare earth magnet around under the paper, and the pile of ORMUS gold will respond to the magnet. The rare earth magnet came from Radio Shack. Here I am holding the magnet in my fingers so you can get a better idea of its relative size. Watch the small pile of ORMUS gold as I start to move the magnet under it. Notice that the ORMUS gold powder is following the magnet. Ordinary gold is well known for not being attracted to magnets. Several gold mining methods take advantage of this fact by separating the heavy magnetic materials from the gold using a magnet. This magnetic material is generally discarded on the mine site. Notice how the ORMUS gold appears to build up a charge from the magnet moving under it, till it reaches some sort of charged state where it is repelled by the magnet and jumps away from it. Now, I've shown this video around to lots and lots of people, including some fairly sophisticated physicists, and nobody's been able to come up with a better explanation than that this is the Meissner effect, that in fact this is a room temperature superconductor. I believe that I'm the first person in human history to demonstrate superconductivity at room temperature on my kitchen table. Of course, somebody else may have done it on their kitchen table, but I'm the first on my kitchen table. This is the behavior that one would expect from a superconductor, particularly a superconductor that wasn't in a rigid matrix. As you can see, this is a powder. If we'd frozen it into a matrix of plastic or something like that, then you would expect it to levitate the whole thing. Superconductivity and other quantum coherent properties have been observed in biological systems. Scientists say that we have superconductors in our brain, but they don't have any idea how they got there or what they are, what's going on. They've actually measured superconductivity in brain tissue, yet they don't know what it is or how it's working. Stuart Hameroff, Roger Penrose, Mae-Wan Ho, Glenn Rain, and others talk of quantum coherence, which is one of the things we were talking about earlier. Quantum coherence being everything being connected. Quantum non-locality, things being everywhere at once, so to speak. That coherence has been spoken of in the context of the body, in the context of the brain, in the context of consciousness. In fact, they say there's pretty good evidence that quantum coherence happens in the body. One of my colleagues in Australia used to be a rocket scientist, and one of the things he was responsible for doing was creating a feedback system so that as the rocket rose into the air and was buffeted by winds, the nozzles, the jets coming out the bottom of the rocket, could adjust so that the rocket didn't fall over. Because, you know, it's kind of a precarious thing having all of the power coming out the bottom. You've got to really adjust that rocket carefully. And you have to have a very, very fast feedback system. Now, nerve impulses travel at about the speed of sound. And he calculated how fast nerve impulses would have to travel in the body in order to play ping pong. Because when people are playing ping pong, that's pretty fast. They're moving fast. And he calculated that nerve impulses couldn't possibly do it. In fact, it was orders of magnitude too slow. 10 times, 100 times, 1,000 times. Somewhere in that realm. It was way too slow. So there's some other communicator in the body besides nerves. And Stuart Hameroff, Roger Penrose, Mae-Wan Ho, Glenn Rain, these are all well-known scientists in the scientific community. They all suggest that this communication system in the body is quantum coherence. Imagine it's like every cell has a cell phone, with the nerves being sort of the hardwired phone for backup, and the DNA being little quantum coherent antennas.